In this video, I'm just going to be really doing some examples of electron configuration and try to prepare you for some possible test questions you may have. I'll try. Keyword is try. Before we get into those examples, I just wanted to talk something specifically about something very interesting in chemistry in general, and that's exceptions. There are a lot of exceptions in chemistry. What would chemistry be without exceptions? And of course, exceptions are going to happen with electron configuration as well. So I have an example here for you. The electron configuration of nickel, which I have wrote conveniently here in the abbreviated notation, it's argon 4s2 3d8. Right next to it is copper. Now with copper, it's argon 4s1 3d10. In theory, should it not be 4s2 3d9 because it's just moving one more in the d block? And yeah, this is what it should be in theory, but it's actually not the case. And you may wonder, well, why? So there's apparently a better explanation for this, but it's way beyond our scope of the focus of this course. And I actually don't know either, but I just know that there's an actual legitimate explanation to explain exceptions for the electron configuration. But for now, all we need to know is that copper and other elements do this because it's more stable for them. So the way to think about it is, so 4s1, let's first draw it out. 4s1, right? And then 3d10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, the explanation I was told in my chemistry class, and technically it's not the right one, but you can sort of just know this for now, unless you choose to pursue chemistry in the future in a university, then there's an actual explanation for that, and for why things are weird like this with copper and other examples. But the explanation we need to know is basically that this is more stable because 3D, remember, 3D is a higher energy orbital than 4s, right? So would it not be more stable if it was entirely filled instead of, let's say, there was just one guy dangling around here, didn't have a buddy, and 4s had one? No, right? So copper just promotes this guy up here, and this guy goes bye-bye. So this is more stable for copper. So this is a weird exception. On your test, I assume you're not going to get asked these. I don't think so. You have to remember anything. I'm pretty sure you don't have to remember any of these weird ones because there are a bunch in the transition metals. The transition metals are pretty much notorious for this, for being the ultimate exceptions in chemistry. And electron configuration is definitely where they show up. Let's look at another example. So V here, I forgot vanadium or whatever it's called. It's 4s2 3d3, and then chromium should in theory be 4s2, argon obviously right here in the brackets. It should be 4s2 3d4, but it's not. It's 3d5 because again that might be more stable for chromium. It'd be better for chromium if all the d orbitals were half filled than for one missing. So if I drew the energy level diagram, right, it's more stable for chromium to be like this, half filled, than to have nobody here and then have a guy here. So that's the general explanation you just need to know for now. If you choose to do chemistry later on, you'll learn the real deal and you'll be like, I see what it is. But till now, just stick with that. Anyways, let's get on to the examples. So the first example is, well, let's say I asked, let's draw the electron configuration of sulfur real quick. So I think I'll just erase all this stuff. You get the idea. You can just rewind if you are confused. All right. Let's say, let's just do the electron configuration for sulfur real quick. Sulfur, okay, 1s2, 2s1, what? I'm bugging. 1s2, 2s2, 2p6, 3s2, 3p4, right? Because 1, 2, 3, 4. Boom. Land on sulfur, right? Let's say I ask you to draw this, the energy level diagram, 1s, 2s, 2p, 3s, 3p, right? Bing, bang, boom, boom, boom. All right. And let's just, draw the electrons. Again, I do this just to demonstrate to you. You should do this as well. Don't just fill them all up, even though you know, just to establish that habit in you. Okay, 1, 2, 3, 4. All right, that's sulfur, right? Pretty straightforward. What would be the not only the electron configuration of S2 minus, but also the the diagram? What would that look like? Pause the video and think about it. So when it's sulfur 2 minus, it means it's gained 2 electrons, right? Gained 2 electrons. Well, if we look in this energy level diagram, what other two places where we could possibly add electrons? Well, in this 3p orbital, there's a spot here and there's a spot here. So these guys just go in here. So what does this then become then? Instead of being 3p4 now, if we count all these, 1, 2, 3, 4, 5, 6, right? Well, it's not like each 2, 4, 6, right? They just total up to 6. So there's 6 electrons here. So for S2 minus, instead of being 3p4, it would now be 3p6, right? It's achieved noble gas configuration. So it's actually the same as argon, right? Because argon has this exact same thing. So pretty straightforward, hopefully. Let's do another one. Let's say I did magnesium. So magnesium, 1s2, magnesium is right here. 1s2, 2s2, 2p6, 3s2, right? Let's draw it out. 1s, 2s, 2p, 3s. So 1s, 2s, 2p, 3s. All right, let's draw the electrons in. Just plug them in. That was English. Plugging them in. All right. Now, magnesium is right here in the alkaline earth. I believe, yeah, the first one's alkaline earth. So magnesium is in this one. Let's do this in a different color. It's in this one, right? So we know it has a 2+ charge to achieve a noble gas configuration. So how does it do that? Well, it loses 2 electrons. So if I asked, well, what is magnesium 2+? Well, where are we going to take off the electrons from? Are we going to take it off from 1s or 2p or 2s or 3s? Think about it. Pause the video and see if you can figure it out. So, if you recall back to the Bohr model, I know, so ancient, we're going back to the Bohr model all of a sudden. When you peel off electrons, do you take them out from the innermost layer? Do you take them off from here? Or do you take them off from here? Well, you take it off from the outermost layer, not the innermost layer. That's wrong. You take it from the outermost layer because that's readily available. So same thing with, electron configuration when you have to account for all these electrons and everything. When you have this 2+ charge, you're going to take it off from the outermost layer. And out of 1s, 2s, 2p, and 3s, 3s is the outermost layer. And that's dictated by the coefficient, aka the principal quantum number, right? 3 is bigger than 2, it's bigger than 1. Hopefully you know that, right? So we're going to take it off from 3s. So what it looked like was basically in magnesium 2+, you don't write this, and there are no electrons here. So it's just like this. And you don't even have to show that. You can just erase this guy. So that's just 2p, like that. So that's magnesium 2+. If we were asked to do its electron configuration and the diagram. Let's do another one. Let's do something fun. Let's do scandium. I'm going to do it in the short notation I showed earlier. So scandium is argon, 4s2, 3d1. Now when we're doing energy level diagram, and I put my argon here. Technically, I'm not sure if this is correct or not, but I just like doing it. It's a little easier than writing it all out. So 4s2 and 3d1, right? Now, what if I asked, one of the charges on scandium is 1 plus. Now, where are we going to peel off the electrons from? Pause the video and think about this. So, again, let's think back to the Bohr model. This is our nucleus. When we're peeling off electrons, right, we're always peeling it off from the outermost layer. Now, you may be tempted to peel it off from 3D because you think that's the outermost layer, but it's not. The outermost layer is dictated by the number n, right? And we know 4 is greater than 3, right? I have 4 cookies, you have 3 cookies, I have more cookies than you, right? Same idea. So we would actually peel off the 1 electron from the 4s orbital and not the 3D orbital, because if the 3D orbital is like this, when it's not, this is just, it's not a circle, it's that weird shape, then 4s is outside of it. Even though 3D may have more energy, 4s is more outside. So don't get confused with that. Don't take it off from 3D. Always ask yourself, which is the most furthest layer from the nucleus, and that'll always be the one that has a greater n value, or a greater principal quantum number, or another way to think about it, a greater row number, right? Because these are rows, 1, 2, 3, 4, 5, 6, 7. Oh, that's a 9. 7, right? So we're going to take off 1 from here. And so this would become, so this would be 4s1 and then 1 plus. So that's scandium. So pretty straightforward, I would say. Let's do a little bit more of an interesting one. Let's say I did lead. Oh boy, this looks weird. This is a challenging one. So let's just start off with writing the electron configuration. So 6s2, bang, 4f14. Again, I do this. You already know why. Let me just check. These are 7. 1, 2, 3, 4, 5, 6, 7. Yes. 5d10. Okay. And then 6p2. This is lead. Now lead also has, it's a multivalent atom. So it can have 2 plus or it can have 4 plus, right? So what would the electron configuration look like? So this one's a little bit of a trickier one. So pause the video and see if you can tell me what would it look like for lead 2 plus. So again, it's all about taking out from the farthest most layer of the atom, right? And so in this case, let's again think, I told you already, it's about the value of n, right? But in this case, we have 2 values that are 6, right? Because 6 is greatest out of 4 and 5 here. We have a 6s and a 6p. So you may be wondering, all right, which one goes first? Which 2 electrons are we going to take out first? And well, if you have a 6s, then the 6p actually goes over it. It goes out, it's the farthest layer actually, compared to s. And you can think about it sort of just looking at the periodic table, right? You start with s on this side and then you end up going to p on this side, right? If that sort of helps to memorize it. So p orbitals will always be more farther out than s orbitals. So you would actually take away 2 electrons from 6p2. So this would be 6s2, 4f14, 5d10. And then I can just take away 2 electrons from here. And then this would be lead 2 plus. Now what about lead 4 plus? Well, if you were able to figure out lead 2 plus, then you can probably easily figure out 4 plus. You're just going to take it away from 6s2, because 6 is more farther out than 4 and 5, right? It's more farther out than the 4f and the 5d orbital. So you take it away from this, and you end up with 4f, 14, 5d, 10. So in lead 4 plus, these 2 go bye-bye. And that's, your electron configuration for, like I showed an example of this multivalent one, and that's all I have for today. So hopefully this all made sense. I think I'm pretty much done with the Electron configuration videos. I might throw in one more. Nah, probably not. I think I'm good. I'm going to move on to the next stuff in this course so I can help you out with those. But yeah, that's pretty much it.